Here we're still dealing with weak acids, but we're dealing with a special type of acids. We're dealing with polyprotic acids. These are classified as such because they have more than one proton that they can donate. In this example, we're dealing with oxalic acid, which has 2 protons that can donate. Usually we deal with this one step at a time. So as you can see down here at the bottom, oxalic acid donates first 1 proton, then the second, in sort of a stepwise manner, which makes our lives a little bit easier to calculate all the concentration of everything present, so long as we know the Ka values, right, for each one of them, and we have some sort of initial concentration. So, dealing with our first deprotonation step, we have an initial concentration of 0.1, and our products, there's nothing there, so we can just write 0. We also know that for every molecule that we lose in our reactant site, we gain 1 in our product site, in each of our products, leaving us with our equilibrium concentrations, the same as what we have been dealing with before. In this case, because it's the first deprotonation, we have to use Ka1. You'll notice once you look at your Ka tables that there's going to be Ka1, Ka2, and even Ka3 for some examples such as phosphoric acid, for instance. So we plug that into our expression. We have this right here, our concentration of products over concentration of reactants, and we make the approximation that the change in concentration is very small when we compare it with the initial concentration, which allows us to get a value of x, right, just like what we have been doing so far. But 8.1 times 10 to the minus 2 is awfully close to 0.1. That's 0.081. So I'm going to compare to see if the assumption holds. Remember that for the assumption to hold, the value of x divided by 0.1 times 100 to get percentage has to be 5% or less. In this case, as you can see, we have 81%. That's a huge, huge number. So much bigger than 5, that means that we cannot make this assumption. So we have to resort to the quadratic equation to solve for our value of Ka, which is what we're going to be doing next. We have here, once we solve for our quadratic expression, we have our value, our polynomial right here, the value of A, B, and C. Plug into our solver or solve by hand, however you prefer. You're going to end up with 2 values of x. One is going to be positive, the other one is going to be negative. We're going to be grabbing the positive because negative concentrations are not a physical possibility. Once we have that, we can go ahead and fill out the chart that we were given, our initial ice table. You have it right here. From there, we can actually move to our second deprotonation step. Keep in mind that it's a stepwise manner, so everything that happened in the first deprotonation is going to affect the second one. What that means is that you're going to start with a certain concentration of protons and a certain concentration of our monoprotonated acid, which is what we have right here. Now, this species is still going to be 0 because it didn't participate in the first dissociation. We fill out the ice table just like we did before. As you can see, we have the minus and the plus. I used y, and the textbook actually uses y as well, simply to differentiate between first and second dissociation. Using our Ka value, 6.1 times 10 to the minus 5, we arrange it products over reactants. We simplify, we say that the change, or that y is much smaller than 0.054, leaving us with this number. And at that point, and this is very common, when you have second and third dissociation, those numbers are going to be really, really small. So usually you can just assume that they are going to be valid. But let's not assume things. Let's go ahead and do the calculation, or the comparison. When we compare our value of x over our initial concentration times 100, we get 0.11%, much smaller than 5%, so we can go ahead and keep assuming that assumption that we just made, leaving us with these numbers right here. Y is going to be our 6.5 times 10 to the minus 5, and from there we can just go ahead and fill out the table and obtain all of the concentrations that were asked for.